Hello class, welcome to Chemistry 115. Today I'll be working through all of the problems on the recitation worksheet for week 15. Feel free to pause the video at any time if you want to go ahead and work on the problem beforehand before seeing what the solution is. Otherwise, feel free to follow along and hear the entire thought process behind solving each problem. So one important thing you'll notice here is that everything written in black are the important pieces of information for the problem. Everything that is written in blue is my work or calculations for solving that problem. And the things that are circled in red are the correct answers to that question. So if you want to compare your answers against mine, you can always feel free to pause the video and look to see what the red circled answers are. Otherwise, you can watch the entire thing and hear the thought process behind solving each one. So let's go ahead and get started. Question number 1 asks us which solution in each pair below has the lower freezing point. 11 grams of methanol in 100 grams of water, or 22 grams of ethanol in 200 grams of water. Notice that the chemical formula CH3OH is known as methanol, or MEOH for short, and the chemical formula CH3CH2OH is known as ethanol, or ETOH for short. Now, in order to compare the freezing points of each of these solutions, we need two important equations, the molality for the solution and also the delta TF equation. You'll notice here on the top left that I've written that delta TF is equal to K sub F times M times I, where delta TF represents the decrease in the freezing point temperature of the solution. Kf represents the molal freezing point depression constant that is unique for that solvent. M is the molality of the solution, and I corresponds to the Van 't Hoff factor of the solute particles. And the second important equation that we'll need is how to calculate the molality of the solution. So molality is determined by dividing the moles of the solute by the kilograms of solvent that we have. Another important piece of information is that the Van 't Hoff factor I is equal to 1 in both cases. This is because both methanol, CH3OH, and ethanol, CH3CH2OH, both do not dissolve to give particles when they're put in water. So methanol and ethanol are not going to dissociate into cationic and anionic particles because they are not ionic compounds. So because they are not ionic compounds, we can therefore assign a value of I equals to 1 to both of these solutes. I've also written out here below that the molar mass or molecular weight of methanol is 32.05 grams per mole, and that the molecular weight or molar mass of ethanol is 46.08 grams per mole. Now, one important piece of information before we start solving the problem is realizing that the larger molality or the larger M value is going to give us a larger delta T sub F value, which would therefore correspond to having a lower freezing point temperature of the solution. Remember that delta T sub F means that it represents the change or the decrease in the freezing point of the solution. So if we have a large decrease, that means we're going to have an even lower freezing point than what we originally had. So to find the solution that has the lower freezing point, we're going to want to find the solution that has the largest delta T sub F value. Going ahead and solving through that problem, here is my work written in blue. So 11 grams of methanol corresponds to 0.343 moles of methanol, and below that 22 grams of ethanol corresponds to 0.477 moles of ethanol. When we divide 0.343 moles of methanol by our 0.1 kilograms of water solvent, we get a solution with a molality of 3.43. And when we divide 0.477 moles of ethanol in our 0.2 kilograms of water solvent, we get a solution with a molality of 2.385. When we compare the two molalities, we can obviously see that 3.43 is larger than 2.385. So since this solution has a larger molality, it's going to therefore give us a larger delta T sub F value, which means that it has a lower freezing point temperature for that solution. So therefore the correct answer is 11 grams of methanol dissolved in 100 grams of water is going to be the solution that has the lower freezing point. Moving on now to part B of question number 1, we can apply this same type of analysis. So part B says 20 grams of water dissolved in 1 kilogram of methanol versus 20 grams of ethanol in 1 kilogram of methanol. Again, I've written out the molar masses of everything, and in this case, I is equal to 1 because the solutes of water and ethanol both are molecular compounds. They're not ionic compounds. So when they are put in our solvent of methanol, they're not going to dissociate into cationic and anionic particles. So because they are non-ionic solutions, we can therefore assign a value of I equals to 1 for both of these. Again, we're going to use the same equation as before, which is the delta T sub F equals K sub F times M times I equation. In this case, for part B, I is equal to 1 again. We're also using the same solvent in both situations. In this case, methanol versus water that we had last time. So being that we're using the same solvent in both of these situations, the Kf value is going to be the same in both equations. So the only point of difference between these two for comparison is the molality. So let's go ahead and calculate that. 20 grams of water, when you divide by its molar mass, is equal to 1.11 moles of water, and 20 grams of ethanol, when you divide by its molar mass, is 0.434 moles of ethanol. In this case, the math is a little bit simpler because our solvents are given to us already in kilograms, so we don't have to do any conversions. And it's a nice easy number to work with, which is 1. So we just divide the moles of solute for each case by our 1 kilogram of solvent. So in this top case right here, we divide 1.11 moles of water by our 1 kilogram of methanol to get a solution with the molality of 1.11. For this bottom case, we divide 0.43 moles of our solute ethanol in our 1 kilogram of solvent, and we find that our solution has a molality of 0.434. Obviously, 1.11 molality is larger than 0.434 molality, so since this solution has a larger molality, it's therefore going to give us a larger delta T sub F value, which means that 20 grams of water dissolved in 1 kilogram of methanol is going to be the solution that has the lower freezing point. Moving on now to question number 2, we're looking at a similar idea or concept. This time we're ranking things. So question number 2 states, rank the following aqueous solutions in order of increasing freezing point. And we have A, B, and C. I do want to point out here that increasing means that we're going to be going from lowest freezing point or the most negative freezing point, to the largest freezing point, or the most positive freezing point. So don't let that confuse you, and I just wanted that to be a point of clarification. So another important thing to realize here is that in this case we need to assume that each solute is going to be dissolved in the same solvent, so that way the Kf value is the same in each case. Being that we're only given the molalities of each of these solutions, we can therefore assume that the solvent that was used to dissolve each of these solutes is going to be the same. If they were different, then the problem would have stated that somewhere, or we would have been given unique Kf values for each solvent. But being that we're just comparing solutions, we can therefore assume that each solution solvent is going to have the same Kf value. So we can ignore that when we're calculating the molalities. Again, increasing freezing point means lowest to highest. And as I've mentioned before, the lowest freezing point is going to be the solution that has the largest delta T sub F value. So when we go ahead and calculate that, we look at part A. So part A, we have a solution of sodium nitrate with a molality of 0.1. When we plug that into our delta T sub F equation, Kf is the same in each case, so we can ignore that variable. The molality is 0.1, and the Van 't Hoff factor I is equal to 2. In this case, I is equal to 2 because we have two components that make up our solution. Since this is an ionic compound, this ionic compound, when it's dissolved in the solvent, is going to break apart into sodium cations and nitrate anions. So since there are two particles or two components of this compound, therefore our Van 't Hoff factor I is going to be equal to 2. Plugging those in, 0.1 times 2 is equal to 0.2 for the delta T sub F value. When we look at part B, we're looking at glucose now. Glucose has a molality of 0.1, and excuse me, and our Van 't Hoff factor for glucose is going to be equal to 1, since glucose is a molecular compound, not an ionic compound. So therefore, when it is placed in the solvent, it's not going to dissolve into positively and negatively charged particles. So we assign I equals 1 to this solution. Plugging that into our equation, 0.1 molality times the Van 't Hoff factor 1 is going to give us a delta T sub F value of 0.1 for the case of glucose. And lastly, for part C, again we have a molality of 0.1 for our solution of calcium chloride. The Van 't Hoff factor is equal to 3 because calcium chloride, when dissolved in solvent, is going to break up into its components, specifically calcium cations and 2 chloride anions. So these three particles gives us a Van 't Hoff factor I equal to 3. Plugging that into our delta T sub F equation, we get 0.1 times 3 equals 0.3. Now when we compare them, we're going to rank them from largest delta T sub F value to the lowest delta T sub F value. Because remember, the largest delta T sub F gives us the lowest freezing point, and we're ranking these from lowest freezing point, or most negative, to highest freezing point, or the least negative or most positive. So in this case, 0.3 is going to be the solution with the largest delta T sub F value, so we put C first. Next is 0.2, which is solution A of sodium nitrate, so that's going to be in the middle. And lastly is 0.1, which corresponds to glucose, so we put choice B as the first. So ranking is going to be C, A, B, in order of lowest to highest freezing points. Moving on now to question number 3, we're going to be doing a different type of math calculation. So in this case, we'll still be using the delta T sub F value or equation, but we'll be using Kf as well. So number 3 states, calculate the freezing point of a solution prepared by dissolving 52.5 grams of lithium fluoride in 306 grams of water, where the K sub F value for water is equal to 1.86 degrees Celsius per molality of the solution. Now, some important notes here is that our ionic compound lithium fluoride is going to dissolve into 2 components, lithium cation and fluoride anion. So that's why our Van 't Hoff factor here is I equal to 2. Again, we're going to be using our delta T sub F equation. We're given the K sub F value for water, and I've also written out the molecular weights or molar masses for both water and lithium fluoride. So with my work here, we start by calculating the amount of moles of lithium fluoride we have in the solution. So 52.5 grams of lithium fluoride divided by lithium fluoride's molecular weight gives me a value of 2.024 moles of lithium fluoride. And 306 grams of water that we're given, I converted that, so we have 0.306 kilograms of water. We take those two values and divide them by each other to find the molality of our solution. So in this case, 2.024 moles of lithium fluoride solute particles divided by 0.306 kilograms of our water solvent is going to give us a solution with the molality of 6.614. So now that we've calculated the molality of the solution, we can go ahead and plug that in to our delta T sub F equation. So for delta T sub F, we already have the K sub F value for water as 1.86. Here is the molality of the solution that we calculated from before. And as I've mentioned earlier, the Van 't Hoff factor for lithium fluoride is equal to I equals 2. So when we multiply these 3 numbers together, we find that the change in the freezing point temperature of the solution is equal to 24.60 degrees Celsius. However, we're not done just yet, because remember, the problem asks us to go ahead and calculate the freezing point of the solution, not the change. So we have now found the change in the freezing point, but we need to find what the actual freezing point temperature is. So in this case, since we're using water as our solvent, we know that water freezes at a temperature of 0 degrees Celsius. So our new freezing point is determined by subtracting our delta T sub F value from the original freezing point of the solvent. So in this case, 0 degrees Celsius minus 24.60 degrees Celsius gives us now a new freezing point temperature of negative 24.60 degrees Celsius as the new freezing point of the solution. Moving on now to question number 4, we're going to go ahead and look at a phase diagram. So question number 4 asks us to consider the following phase diagram. Part A says identify the process occurring as one goes from point C to point D, and to identify the process occurring as one goes from point E to point F. Now, an important thing here to realize is that this is the phase diagram for water. This is a classical or common phase diagram that's seen and used in many chemistry textbooks. So you should become familiar and memorize the phase diagram for what that looks like for the case of water, being that it is a very common and simple one. For example, on a test, we might give you a different phase diagram for a different chemical, but if so, we would tell you what that compound is in advance. But otherwise, if we don't tell you, it's most likely the case of water. So I went ahead and redrew the phase diagram for water, and I labeled all of the parts. This leftmost region right here is the solid phase of water. This in-between region is the liquid phase of water, and the rightmost region over here is going to correspond to the gaseous phase of water. So part A asks us to identify what happens as we go from C to point D. Looking at our phase diagram for water, when we go from C to D, we notice that we're transforming from the solid phase to the gaseous phase. So we go from solid to gas without traveling through the intermediate phase of the liquid. So since we're going from solid to gas, that corresponds to sublimation. Part B asks us to identify what is going on as we go from point E to point F. So in this case, when we go from point E to point F, we are traveling from the liquid region to the solid region without going through the gaseous region. So when we go from E to F, we are transforming from a liquid to a solid, and that process is called freezing. Moving on now to question number 5, we're given a diagram here that corresponds to the different types of unit cells that we've seen in class. Here we have a simple cubic unit cell, a body-centered cubic unit cell, and a face-centered cubic unit cell. Question number 5 says to match the 3 basic unit cell types to the equation that represents the number of atoms in that unit cell. So for this type of question, it's mostly just a matter of memorization and remembering which one has how many atoms. So in this case, for choice A with the simple cubic unit cell, that's going to correspond to Roman numeral I, because a simple cubic unit cell has 1 atom total within that unit cell. And when we look at equation for Roman numeral I, it tells us that the number of atoms is equal to 1/8 times 8. Well, 1/8 times 8 is equal to 1. And this is because we have 8 different vertices in our cubic unit cell, and each of those vertices represents 1/8 of an atom. So if we have 1/8 of an atom at each vertex, and we multiply that by the 8 vertices in a cube, that gives us a total of 1 atom in a simple cubic unit cell. Moving on to part B with the body-centered cubic unit cell, that's going to correspond to 2 atoms, which matches Roman numeral 3 here. So Roman numeral 3 says that the number of atoms is 1 plus 1/8 times 8. 1/8 times 8 is equal to 1, and 1 plus 1 is equal to 2. Now when we look at the body-centered cubic unit cell, again we have our 8 vertices, which each correspond to 1/8 of an atom. So 8 vertices times 1/8 of an atom gives us 1 atom. But you'll also notice here that we have another atom within the center of our unit cell. So this sphere here represented in the middle is equal to 1 whole atom. It's not equal to a fraction. So 1 whole atom plus another atom, when we add up all of these vertices, is going to give us 2 atoms total for the body-centered cubic unit cell. And lastly is the face-centered cubic unit cell. That corresponds to 4 atoms total, which is represented by Roman numeral 4. So when we look at IV, the equation for the number of atoms is equal to 1/2 times 6 plus 1/8 times 8. When we look at the face-centered cubic unit cell, we can see that again, like before, we have 8 vertices, each representing 1/8 of an atom. So that's one atom right there. However, we have these yellow or gold atoms on the face of each side of the cube. So each face represents 1/2 of an atom. We have the front and back faces, top and bottom faces, and left and right faces of our cube. Those 6 different faces, each of them representing 1/2 of an atom, when we multiply them together, we get 3 atoms that are represented by all of the faces combined in our face-centered cubic unit cell. And again, the vertices all add up to 1 atom. So therefore, 3 atoms plus 1 atom is equal to 4 atoms for the face-centered cubic unit cell. And again, this is simply just a matter of memorization and remembering that the simple cubic has 1 atom, the body-centered has 2, and the face-centered has 4. Moving on now to question number 6. Iron crystallizes in a body-centered cubic structure. If the atomic radius of iron is 126 picometers, find the edge length in nanometers of the unit cell. So you can see here that I've drawn a body-centered cubic structure, so that way I wouldn't have to be scrolling up, so that way you can see what it looks like without me constantly scrolling. So hopefully this crude drawing gives you a rough idea of what we are dealing with. So this red circle or sphere here in the center is supposed to represent 1 atom, and each vertice represents 1/8 of an atom for a total of 2 atoms. Now I've written here L equals the edge length. This is the variable that I'm going to use to represent one edge of our cube, and the formula for that is equal to 4r over the square root of 3, where r represents the radius of an atom. And the derivation for this formula involves using algebra and geometry, so I'm not going to show those mathematics here. However, feel free to look at your lecture notes or read the textbook to see how some of these equations are derived for different types of unit cells. But in this case, we're just going to go ahead and use the formula to calculate our final answer. So we are told that the radius of our iron atom is 126 picometers. So when we plug that into our formula and multiply things out, I get a value of 504 picometers divided by the square root of 3. And then when you divide that by the square root of 3, you get a value of the edge length equaling 291 picometers. However, we're not finished just yet because, as the problem mentioned, we need to convert that into nanometers. So we need to find the edge length in nanometers for this unit cell. Doing dimensional analysis, we multiply 291 picometers by 1 times 10 to the negative 12th meters. That'll cancel out our units so that our answer is in meters. And again, 1 meter is equal to 1 times 10 to the 9th nanometers. So multiplying everything out, we get an edge length for this unit cell equal to 0.291 nanometers. So the edge length for our body-centered cubic structure is equal to 0.291 nanometers. Moving on now to question number 7, the last problem in this worksheet. We're going to be doing some more chemistry calculations. So question number 7 says, an element crystallizes in a face-centered cubic lattice and has a density of 1.45 grams per centimeter cubed. The edge of its unit cell is 4.52 times 10 to the negative 8th centimeters. Now part A asks us how many atoms are in each unit cell. As I mentioned before, this is just something you simply need to memorize. So a base-centered cubic lattice is always going to have 4 atoms in it. So that's the answer to part A. Part B says, what is the volume of this unit cell? If we remember from geometry, volume is equal to length times width times height. However, since we're dealing with a cube, we know that the length, width, and height of a cube is all going to be the same. So we can rewrite the volume equation as simply the edge length of our cubic unit cell raised to the third power. Notice how the edge length of our unit cell is already given to us in the problem as 4.52 times 10 to the negative 8th centimeters. So we plug that into our formula and we cube that to get a volume of 9.235 times 10 to the negative 23rd centimeters cubed. So that is the volume of our unit cell. Part C asks for the mass of our unit cell. Now to determine that, we need to remember the formula for density. Density is equal to mass divided by volume. You can see here that I've rewritten the equation to solve for mass. So mass is equal to density times volume. We know that the density of our unit cell is given to us as 1.45 grams per cubic centimeter. So there's that piece. The volume is the answer that we calculated from the previous part. So in part B, we got 9.235 times 10 to the negative 23rd centimeters cubed. Multiplying out the density by the volume, we get the mass as 1.339 times 10 to the negative 22nd grams. And realize that this is the mass of the unit cell, not the mass of the atoms within the unit cell. There is a difference. And finally, part D asks us to calculate an approximate atomic mass for this element in AMU, and we need to determine what that element is after we know what the AMU value is. So in part D here, we have that 1 unit cell is equal to 1.339 times 10 to the negative 22nd grams in this case. To find what that mass is per atom, we know that one base-centered cubic unit cell has 4 atoms in it, so we're going to divide this by 4. To get our units of grams to kilograms, we divide by 1,000. So divide by 1,000 because 1,000 grams is equal to 1 kilogram. And the last piece in our dimensional analysis is converting it to AMU. So as given to us in the problem, 1 AMU is equal to 1.66054 times 10 to the negative 27th kilograms. So using that piece of information in our dimensional analysis, we multiply everything out and I get a value of 20.16 AMU. When you look on the periodic table of elements, you can see that 20.16 AMU corresponds to the element neon. With that being said, we have now solved all of the problems on the week 15 recitation worksheet. I hope that you've found this work through of all of the problems helpful, and that way you can understand the thought process. Another thing I do want to bring to your attention before I go is that notice how on each problem, or most of the problems here, there are numbers that are written in parentheses. This corresponds to the chapter and section number in your chemistry textbook and the page number that you can find this on for similar problems if you want extra practice. Not all of these problems, however, have similar problems that are worked through in the textbook. However, if you do have questions still, or other related questions, then feel free to go ahead and contact us. But other than that, I hope you found this helpful, and let us know if you need anything. Otherwise, stay safe, everyone, and I wish you good luck on your final exam. All right, goodbye.